Okay, so we just looked at what was happening when we were looking at a limit graphically as you approach some value and if it exists or not. So now we're going to look at this algebraically. And so first of all, let's just go through the definition again, the intuitive definition. The limit as x approaches a of some function f of x is equal to L is computed by making f of x values arbitrarily close to L, not equal to L, by restricting x values sufficiently close to A. No, f of x is defined when x is near the number A. Okay, so it might not be defined at x equals A itself, and we saw that, but it's is defined there. So for instance, again, let's just look at a graph. You have some value, in this case it said A, maybe you come down here, it might not exist there, it might have an open circle there, or it might be closed. But as we get closer and closer here, that Y value we're getting is L. Okay, so if you look at this, so let's look at the limit. We want to find the limit as x is approaching 1. So we have to make sure that the numbers as x is approaching 1 on the left is going to give us back the same value as the limit as x is approaching 1 on the right. Normally when we're doing limits, you want to do direct substitution. So for instance, in this case, I have the limit as x is approaching 1 of x minus 1 all over x squared minus 1. And so direct substitution, this is usually the first place that you want to start. And if it doesn't work, then what we're going to be doing next is helpful. Also, what we're doing next is kind of giving you an intuitive what's going on. So let's go in here, and wherever we see an x in our function, we're going to plug in 1. And because I'm plugging in that number wherever I see an x, I no longer want to write that limit notation. So once you plug that number in wherever you see an x, drop the limit notation. So I'm going to put a parentheses wherever I see an x. So I see an x, so parentheses minus 1. In the denominator, I see an x squared, so parentheses squared minus 1. Go in here, replace it with a 1 inside the parentheses. Order of operations, PIMDOS. Simplify numerator, we get 0. Denominator, we get 1 squared minus 1, which is also 0. This is something that's going to happen quite a bit while we go through this course, where you get this form of 0 over 0. This is called an indeterminate form. If this happens when we're doing direct substitution with limits, then it's not telling us. We don't know what's happening at that x value, or what that y value is. And we have to go back in, and we either have to manipulate this value, in this case, this rational expression, so that we don't get that form anymore. I'll give you different tools on how to do that through the course. Or we can see by direct substitution. So let's look at what's happening direct substitution. So basically, when you're choosing values of x which are smaller than 1, you're technically looking at the limit in this case as x is approaching 1 on the left. So with that superscript of a negative of our function. So this is where it could get really tedious if you have to go in here and wherever you see an x, keep on trying different numbers and plugging it in and simplifying it. And so this could be helpful to use Desmos or a graphing calculator if you own one. So numbers close to 1, I would let's plug in 0.5. Not too close, but it's close enough. Something else that's close to 1, maybe 0.9. How about 0.999? And then maybe 0.9999. I mean, we can go on forever with those 9s. And we want to go in, plug it in wherever we see an x. And we want to see, is that y value we're getting back in all of those cases going to one particular y value? So I pulled up Desmos, and okay to use this on your homework. I'm going to go to the math tools I'm going to scientific calculator. I want to define my function. And so f of x, so you have to make sure you have parentheses in the right place. So it was x minus 1 in the numerator. So I need parentheses around that whole numerator. So x minus 1, all divided by x squared plus 1. So x caret 2, get out of it. I'm going to push the arrow to the right, minus 1. And then we're going to go evaluate it. We said at 0.5. And so notice over here, I have 0.66666666 all the way. So, and I could get what it is in fraction form, which doesn't really help me see what that is going towards. So let's see if I get even closer to 1 on the right. So we said f of, I don't remember what I said, 0.8. Okay, there's a little difference here. This is 0.5555. So let's even get closer. So how about f of 0.9? Okay, so from a 0.55 to a 0.526, f of 0.99. So 0.50. So you want to keep doing this until you start getting things that look almost exactly the same. So 3 9s, look at, I have 0.50 on both of those. It looks like it's heading towards something. So doesn't it look like it's going towards 1/2 here? The more 0.9 and then the 9s after that I put in, notice that that's going to a 1/2. And so I can say then that the left-hand side limit as x approaches 1, notice if I put 1 in here, it's going to tell me it's undefined. I already knew that because it sets the denominator 0. But as I get closer and closer, I'm reaching a 1/2. Okay. So going back here, it's gone. I get a 1/2. So let's look at what's happening on the right. So right-hand side of 1, I just want to make sure that it's coming into the same value. So number bigger than 1, so what about 1.5? So a number bigger but closer to 1 than 1.5, so maybe 1.25. So I got a 0.4, 0.444. Now let's do 1.1. That's even closer to 1 on the right, and that should be undefined because I have 2 decimals. So that's 0.476. If I look at 1.01, even closer to 1. So it looks like, again, I'm approaching a y value of a 1/2 as I get closer and closer to 1 on the right. So if I did 1.00001, I'm getting closer and closer to 1/2. And so left and right-hand side limit are approaching the same y values. Okay, so we saw these values right here, right? We're getting closer and closer on the left to 1/2. We also saw when we plugged in numbers here, so we saw 1.5, 1.2, we saw 1.1, 1.00001. We saw that these also went to 1/2. So 1 on the right of f of x equals 1/2. Notice if we had manipulated this limit first, we would have seen that. Notice that that denominator is a difference of squares, so we could have factored that. And that would have been one way to do it. So let's just look at that. So we could have set the limit as x is approaching 1 of x minus 1 all over x squared minus 1. We can rewrite that. The limit as x is approaching 1 of x minus 1 all over difference of squares. So let's just factor that. So x minus 1, x plus 1. Notice you have common factors in the numerator and denominator that can cancel. And so if we canceled here, we would be left with a limit as x is approaching 1 of 1 over x plus 1. Let's just go in, do direct substitution. Wherever we see an x, we're going to replace it with that 1. And so this is equal to, and when we do the direct substitution, we're not writing the limit anymore. So we get 1 all over 1 plus 1. And if we simplify, we get 1/2, which we had seen when we were doing it by plugging in values really, really close to left and right. So really quick, I want to show you the graph, and then let's see where we're at. Maybe we'll try one more. Okay, so we just graphed this function on Desmos, and we were looking at the limit as x is approaching 1. And so if we look at this and we zoom in here, when x is approaching 1, so notice our y value is x is approaching 1. Oops, didn't mean to do that. If I come in on the right, I'm getting 0.521, I get 0.51. If I hit, really there should be an open circle on this graph. If I hit 1, it should tell me it's undefined. I don't know if I can show it. I don't know if it passed it. There, 1 undefined. There should be an open circle here, but basically what your computer program is doing is it's getting really, really close to that x equals 1, and it's seeing that that y value is 1/2. Okay, so that's what's happening graphically. We just showed it algebraically by plugging values in. We showed it by manipulating our function to let it fall out to 1/2. Okay, so let's